Okay, so we'll have a couple parts to this. So this is just number one in a series. So in the first part, I'm going to give kind of a motivation, big picture overview of what we're doing, how we're doing it, why we're doing it this way. And then in the second part, Barry is going to give a more hands-on tutorial on how to use one of the two packages that we just released, the C++ package. It calculates part of the source for the second order metric perturbation in this whole formalism. So that will make a lot more sense once I give the big picture overview. Okay. Do we have it so everyone's auto muted when they join? Hearing a little bit.
I think so, yeah.
Okay, great. Okay, so let me hide the video panel. So Niels will also answer any simple questions during my talk and help with technical issues during Barry's portion. But we do hope to make this interactive, so hopefully you'll ask a lot of questions and Niels will pass on some to me that are especially interesting, or maybe things he thinks I'm best able to answer. Seem to have lost the screen share. Okay, got it back. There we go. Okay, so big picture. So Niels and Barry and I have wanted to put on workshop series like this as part of our roles in the LISA consortium work packages for quite a while. It's just taken us a long time to get around to doing it. So we're really going to be covering stuff that Niels and Barry and I have developed over the past 10 years, a lot of mathematical and numerical infrastructure. And we've had also important key contributions from Leanne Durkin and Jeremy Miller. And the stuff we'll be focusing on in these workshops is really the contribution of these 5 people here. But we do also have a bigger group of collaborators working on second order developments. And I'm just listing them here. So hopefully most of them are actually also in attendance and can answer questions. Okay, so here we go. So just an outline. Why are we talking about this? What's the purpose of these workshops? Then I'll very quickly, or hopefully quickly, go through what I'll call regular perturbation theory, which is just Taylor series in a small parameter beyond linear order. So probably everyone who's attending has some level of experience of linear black hole perturbation theory, or at least they're familiar with the basic idea. Probably a much smaller subset of people here have any experience with nonlinear black hole perturbation theory, specifically a second order. So I'll go through a bit of that and what goes wrong with a regular perturbation expansion in the context of self-force and small mass ratio binaries. I'll then outline what we actually use in practice, which is not regular perturbation theory. It's something called a multi-scale expansion. Probably after this, or maybe even earlier, I'll hand it over to Barry for the hands-on portion because he's kind of time constrained today. And then I'll come back to a very quick summary of the derivation of what he'll actually show you how to use. But maybe I'll also have time to do this before he takes over. Okay, so a lot of people are actually a bit confused about what we mean by second order, what we mean by post-adiabatic. It's hopefully not going to be confusing once we're finished. So I think everyone gets the basic idea that we are expanding in powers of the binary's mass ratio. So we have a small body with mass little m orbiting around a big black hole with mass capital M. And so we define this to be a small parameter, epsilon. We assume it's much less than 1. And then we expand the metric of the binary in powers of epsilon. So this is the exact space-time metric. This is the background. Lots of stuff that we do is in Kerr, but everything in this workshop is going to be entirely Schwarzschild background. So this G here is always going to be a Schwarzschild spacetime. So we have a very slowly spinning primary black hole in the binary. Then we have perturbations produced by the small object. So first order, and of more interest here, second order perturbations. Now, how does this relate to adiabatic and post-adiabatic orders? So this nomenclature comes from Hinder and Flanagan, who first did a 2 timescale analysis of small mass ratio binaries. And what they found is that on the radiation reaction time, which means the time over which the binary significantly evolves, and that time is of order 1 over the small parameter. So the evolution is, slower and slower for smaller and smaller mass ratios. The waveform phase has an expansion that looks like this. So it starts at order 1 over epsilon. That's because if you wait a long time, you accumulate a lot of phase. So after a time of order 1 over epsilon, you have a phase accumulated of order 1 over epsilon. And then you have 0th order correction and smaller corrections. And all these coefficients depend on epsilon times t, so that when t is of order 1 over epsilon, these arguments are of order 1. And the thinking is, and the goal in the cell force community has been for quite a while, that we need both of these terms. We need to do all our expansions sufficiently high order to capture both of these terms, phi 0 and the phi 1. And the thinking there is if we're missing something of order 1, that could be a radian, it could be 10 radians, so that'll screw up parameter estimation. But as long as we have this term, then the thing we are omitting, the next term, should be small, especially for emery, 10 to the minus 5, so very, very small. And as I'll show you in a second, probably quite small even for mass ratios around 1 to 10. Okay, so this first term is called adiabatic order, kind of for historical reasons. This is often described as coming from the dissipative part or some averaged dissipative part of the first order cell force. But just to relate it to this expansion here, I'll just say it's coming from the oscillatory piece of H1, or the radiative piece of H1. So to get this leading order phase evolution, you don't need all of the first order metric perturbation, you need just a specific piece of it. Then this next term we call first post-adiabatic order, or 1 PA. So adiabatic is 0 PA, and first post-adiabatic is 1 PA. Well, this is determined by the oscillatory piece of H2, just like the 0 PA term was determined by the oscillatory piece of H1. But you also need the entirety of H1 now. You can't get away with ignoring any part of it. So we often interchangeably refer to second order and 1 PA, second order or first post-adiabatic order. That's because we solve the Einstein equations through second order to get 1 PA approximation to the waveform phase. Okay, so that's what we're talking about. We're talking about generating waveforms at 1 PA order by solving the Einstein equation at second order. Now, why do we want to hold these workshops now? Why is this a kind of a pivotal moment? Well, after many years, we actually now have these 1 PA waveforms for the first time. So that's in this letter from a year and a half ago. And I'll send around these slides after the workshop, and you'll find that all of these archive numbers are all clickable hyperlinks, so they'll all take you to the archive. So yeah, we've finally put together these waveforms. This is just an example I usually show for mass ratio 1 to 10. This is for quasi-circular, non-spinning binaries, which is the only case that we've actually got completely done. And so here I'm comparing the 1 PA post-adiabatic waveform in orange against numerical relativity waveform from the SXS collaboration, which for these purposes we can think of as just the exact waveform. This is particularly the 2-2, L equals 2, M equals 2 mode of the waveform. And here you see that, as I said, at mass ratio 1 to 10, we get very good accuracy. So here it's, I don't know, 0.2 or 0.3 radians of error or something like that. The letter, of course, is very short on details. If you want more details, and in particular, if you want a discussion of the accuracy of these waveforms more than just looking at pictures like this, this paper that we put out with a couple of EOB collaborators last year does a pretty comprehensive error analysis of our waveform. And one thing to note is that even though our waveform looks great, we know we're actually doing a couple things wrong. We just think that they're numerically small effects, and that's discussed in this paper. And the paper doesn't actually contain this error estimate, but you can extract this error estimate from the results in the paper. And so we find that the phase error, so this next term, what would be a 2 PA term, the error that we are omitting by generating a 1 PA waveform, that error is 7.5 times epsilon radians, roughly, for an inspiral that starts at 20 M and inspirals down to the ISCO. To get technical, the M here is the total mass in both these figures, whereas the M back here was the primary black hole mass, but it's not too big a difference. Okay, yeah, so that tells you that this term that we were omitting, it could have had a coefficient of 1,000, so it could have been 1,000 times epsilon, and could have been a huge effect and a huge error. But we find that no, even for a long waveform starting from 20 M, it's a few radians times epsilon. So for mass ratio 10 to the minus 5, it's an incredibly tiny effect. Now, another important thing about these waveforms is not just that they're accurate, but they're also fast. So we can generate these waveforms in a few milliseconds for any mass ratio and for basically any number of cycles, because what determines our limitation is not the number of cycles, it's the total orbital radius or total change in orbital frequency, which doesn't care about the number of cycles. So this is fast enough ultimately for data analysis, and with Ollie Burke and others, we are now actually doing parameter estimation studies using these waveforms. And Niels has put most of this waveform model into Few, the fast Emery waveforms package. And I think we will release that to the public by the end of the year, probably. I say most of the waveform because it's got the phase, but it doesn't have the second order corrections to the amplitudes. But you usually don't care about that anyway. Okay, so that's why now this goal that we've been trying to reach for the past 20 years or so of getting second order waveforms has now been achieved. And we hope that the entire Cellforce community and maybe more people who are interested in getting into the community will start reproducing these results, making use of these results, building their own calculations that hopefully are better than ours, because we did a lot of silly things along the way. So we think the time is good to start showing people how exactly we did these calculations so that they can not just make use of the calculations, but reproduce them, build on them, and do better than them. Okay, so what are we going to cover in these workshops over the next few months? So not so much general second order Cellforce results, not so much general multi-scale expansions. It's going to be really focused on what goes into the calculation of that waveform I just showed you. So this is solving the Einstein equations through second order for quasi-circular, non-spinning binaries with small mass ratios. Hopefully, as we progress through these workshops, we will add papers explaining more of these steps. So we've been terribly slow in putting out papers explaining what we're doing. As you can see on these bullet points, we have a few papers out, and one more should be coming out in the next couple of weeks. And hopefully by the time we finish all these workshops, we'll have most or all of these bullet points covered by papers that you can refer to. So what goes into solving the second order Einstein equation, or solving the Einstein equation through second order for these types of binaries? Well, the first thing is a multi-scale expansion of the Einstein equations. So just an overall formulation of the Einstein equations. And that was discussed in great detail in this paper that I wrote with Jeremy Miller a few years ago. And that is the formulation that we are using. Then once you've formulated the field equations, actually by far the hardest part of the whole calculation is actually just calculating the source or all the sources that appear in the second order equation. So the equation for the second order metric perturbation. There are basically three types of sources, and you'll have a better understanding of them by the end of this workshop. There's a piece we can calculate by coupling together first order modes to calculate a mode of the second order source. There's a part that comes from the slow evolution of the first order modes. And then there's a complicated construction involving punctures and effective sources near the location of the particle. Now, once you've calculated the sources, there's still more work to do because we need boundary conditions. And in this formulation, boundary conditions are highly non-trivial at second order. And that actually involves introducing new punctures and doing special things to calculate the sources near the boundaries. Once you've got your sources and you've got your boundary conditions, then you can solve your field equations. And we use a particular setup for that, and we'll put out a paper on that, as I said, in a couple of weeks, hopefully. And ultimately, we generate waveforms. So in today's workshop, the goal will be to cover overview, big picture, multi-scale expansion. How do we formulate the field equations? And then what Barry will cover in the more hands-on part of the workshop is this mode coupling source. So you have a whole bunch of first order spherical harmonic modes, and you want to couple them together to get modes of the second order source. And he will go through one of the packages that we quickly described at Capra, and he'll show you how to actually use it. And hopefully by the end of the workshop, some or all of you will have actually installed it and used it and looked at this source. Okay. Now, as I said, before I get to the multi-scale expansion, I want to say just some general things about second order perturbation theory and what goes wrong if you don't use a multi-scale expansion. So this kind of motivates why we formulate the field equations the way we do. Okay, so if you're doing regular perturbation theory, what I mean by that is you take your metric and you take your stress energy tensor, or whatever other fields you have in the problem. You think of them as functions of space-time coordinate values, x mu, just labeled as x here, and of your small parameter epsilon in this case. And then you just do a Taylor series in powers of epsilon at fixed coordinate values for the metric and for the stress energy tensor. So this is the simplest way of doing perturbation theory. Now, if you have an expansion of your metric that looks like this, then if you substitute that into the left-hand side of the field equations and expand everything out in powers of epsilon, then you get a leading order term that is just the Einstein tensor of the background metric, plus the term that I would guess everyone on this call is familiar with, which is the linearized Einstein tensor constructed from this first order perturbation. Now at second order, you get another linear term, exactly the same linearized tensor, but now constructed from H2. But now you also have quadratic products of H1. So I'm calling that delta squared G H1, H1. So two arguments to show that it's quadratic in H1. If you've never seen that, let me just quickly show that to you. So almost all the equations I'm going to show can be found in this paper with Jeremy Miller. So let's open that up. So somewhere down here, we will see the quadratic term in the expansion of the Einstein tensor. So here I'm writing it as the trace reversal of the quadratic term in the Ricci tensor. And that looks like this. So here H is just a generic perturbation. In our case, this is going to be H1, H1, H1 everywhere. And you see it's products of covariant derivatives of, in our case, H1. The bar here denotes trace reversal. So this term here is the trace reversed perturbation. Indices are raised with the background metric as usual in perturbation theory. And semicolon is the covariant derivative compatible with the background metric. So it's not that complicated. It's just a sum of products of derivatives of the first order metric perturbation. So you have some terms that are derivative times derivative. You have some terms that are just the field times second derivative. You never have more than two derivatives. Okay, let's jump back to the talk. So if this is now your left-hand side of the Einstein equation, and this is your right-hand side, or 8 pi times this is your right-hand side, then you can just equate coefficients of powers of epsilon. So the epsilon to the 0 term is just the vacuum equation for the background. And for us, this is just the Schwarzschild metric, which trivially satisfies this equation. Then we've got the linearized Einstein equation with H1, and it's sourced by T1, the first order stress energy tensor. So for us, this T1 is a point particle, a point mass, moving on a geodesic of the background spacetime. So I'll get back to the point in a moment. So you have a point particle moving on a geodesic, sourcing H1. Then a second order, we have the same linearized Einstein tensor, but now constructed from H2 on the left-hand side. We move the quadratic term to the right-hand side. So your first order fields are now acting as a source for your second order field. And again, we have now the correction to that point particle stress energy tensor. So this is just a sequence of equations. The left-hand side is always the same, well, beyond the 0th order one. Left-hand side is always just a linear operator acting on your perturbation, and all that changes is the source. So you might think this is a very easy problem. We know how to solve this equation. Surely we can easily solve this equation. It's exactly the same left-hand side. Now, to explain what goes wrong in ordinary perturbation theory, let me talk about the form of the stress energy tensor. So I'm going to break up my coordinates into t and xi. So xi is the set of spatial coordinates, which will be r theta phi for most of this talk. And the particle's orbital trajectory is, a t component, and then spatial coordinates as function of time. Now, you can write down a stress energy tensor that makes sense in the first and second order field equations in the small mass ratio limit. Proving it actually makes sense is quite a bit of work, and even using it is quite a bit of work, and we have not used it ever in practice at second order. But it makes it a bit easier to explain what's going wrong, what is going to go wrong here. So this is just an ordinary point particle source. I should have a mass out here, the mass of the particle. So it's a point mass, delta function source. This is an integral over the world line. This is the determinant of the metric. And so if I change my integration variable from proper time here to coordinate time t, I can get rid of one of the delta functions, get rid of the integral, and I'm left with a three-dimensional delta function on space that's supported at the position of the particle at each moment of time. Here, all these tildes and everything mean that all these quantities here, the metric, the proper time, the forward velocity, they are all defined in an effective spacetime, which is a vacuum spacetime, not the physical metric. And this effective spacetime is the background metric, Schwarzschild, plus the Detweiler-Whiting first order regular field, plus the second order regular field, etc. And so this stress energy tensor was first written down by Detweiler, and so we refer to this as the Detweiler stress energy tensor. And the validity of it was proved in this paper by myself and my student Sam Upton a couple of years ago. So the second important thing here is the trajectory. What governs the particle's trajectory? It's an equation like this. So this equation is equivalent to geodesic motion in this effective metric. So if it were just a test mass, it would move on the geodesic of the background Schwarzschild metric. But because it's not a test mass, because it's gravitating, it instead moves on a geodesic of this effective spacetime, this g tilde. So here I'm writing the covariant acceleration of the trajectory in the background spacetime. So this capital D denotes a covariant derivative along the world line in the background spacetime. And now on the right-hand side, I have a whole bunch of things constructed from HR. HR here is the sum of epsilon HR1, epsilon squared HR2, and so on. So this right-hand side is what we usually refer to as the self-force, or the self-force per unit mass. Self-acceleration, all equivalent statements. Okay, so we've got a stress energy tensor here with a point mass moving along some trajectory, and that trajectory is governed by this self-forced equation of motion. Now, if we're doing regular perturbation theory, meaning we're expanding everything in powers of epsilon at fixed space-time coordinates, then one of the things that gets expanded is the orbital trajectory itself. So it's a function of coordinate time and epsilon, and you expand this out. So here, concretely, I'm going to take r theta phi as my spatial coordinates. These are just the usual Schwarzschild spatial coordinates. And what you find is, if you're trying to describe quasi-circular orbits that are almost circular, with an expansion like this, what happens is this leading order term is just geodesic. So it's at some fixed orbital radius, r0, that doesn't depend on time. Let's put it on the equator, or choose our coordinates such that it's on the equator, pi over 2. And its azimuthal phase, phi, is omega t with a constant frequency omega. So this is just the usual circular geodesic that we all know and love. Then the next term is where things go wrong. So you find that if you substitute this into this accelerated equation of motion, the next term looks like this. So you get some constant correction to the orbital radius, you get some constant correction to the orbital frequency. So these are both dictated by the conservative first order self-force. But then you also get growth in time coming from the first order dissipative self-force. So the orbital radius changes linearly with time, forever, for all time. And the orbital phase changes quadratically in time for all time. So these A2 and B2 are constant coefficients. So you can imagine, see if I can get this annotation working. Let's go. So leading order trajectory is just a circular orbit. And then we're adding this correction x1, which we're assuming to be small when we write down an expansion like this. We're adding this correction that is, driving the in-spiral inward. So x1 is entirely responsible for this in-spiral. X0 is just a permanent circle. Then we see that x1 grows large with time. So if you wait long enough, this expansion is broken because these supposedly small corrections are no longer small. So you don't want to use an expansion like this, but it gets even worse once you look at the Einstein equation. So let's see how that happens. So at first order, we have this nice simple stress energy tensor where it's a three-dimensional delta function supported at the particle's position. The phi p, the orbital phase, is just omega t. And this is what everyone, or almost everyone in the audience here, probably has used in the past, or something derived from it. It's a very simple source to put into the Einstein equation. It's very simple to solve the Einstein equation with this source. So in a Schwarzschild background, what we do is we decompose into tensor spherical harmonics. So these are just tensorial generalizations of spherical harmonics. We'll get into what particular choice we're using a bit later. I here runs from 1 to 10, so there are 10 linearly independent spherical harmonics, or 10 linearly independent tensor spherical harmonics for each L and M. And if you just decompose this stress energy tensor into a basis of harmonics like this, well, you get a radial coefficient, which is going to be just a radial delta function. You get this exponential, e to the minus im omega t. So that comes from this omega t right here. And then you get the angular dependence. So this has a very nice, simple Fourier spectrum. It's a discrete Fourier spectrum. All the frequencies in it are multiples of omega, of the orbital frequency omega. And then this motivates adopting basically exactly the same form for the first order metric perturbation. We have radial coefficients. We have the same set of frequencies, m omega, and our spherical harmonics. So when you substitute these two expansions into the linearized Einstein equation, you just get simple second order radial ODEs for each of these coefficients H1 ILM. And that's been looked at, for decades, but in our particular choice of basis and a particular setup, this paper goes through it in detail. So at first order, everything looks beautiful. At second order, everything goes wrong. So I said that the correction to the orbital trajectory is growing quadratically with time. And this stress energy tensor has the trajectory right inside it. So when we expand this out, the T2 is going to have this same quadratic growth in time. So the source on the right-hand side of the Einstein equations is growing with time. And suddenly we don't have a nice discrete spectrum. We have a horrible mess because we have things that are that don't have a continuous spectrum. So if you try to go to the frequency domain, you just get a mess. Even if you're trying to solve in the time domain, you're just going to get things that blow up with time. H2 itself is going to blow up with time. Everything blows up with time. So it was always well known that you probably wouldn't want to use a formulation like this when going to second order. This is just to explain why it's bad. So what do we use instead? We use a multi-scale expansion. That can mean a lot of different things. I'm going to present a particular form, which is the form we use in practice. So what's the motivation? we want to construct an ansatz that captures the features of the real physical problem we're trying to model. So we want a quasi-circular inspiral, which means we want something that's almost periodic, but it has a slowly evolving frequency. So the way we're going to do that is we're going to start thinking of everything as being a function on the phase space of the orbit. So the phase space is, the xi and x dot I, the position and velocity, basically. And when we say we're making it quasi-circular, we're basically reducing the dimensionality of the phase space so that we just have two coordinates on the phase space. We have phi p, the azimuthal phase of the particle. Let's call that the fast coordinate on phase space. So it's evolving on a time scale, basically 1 over frequency, so the orbital time scale. Then we have a slow coordinate on phase space, which is something that's changing slowly with time. And that's the phi p dot. And we're just going to define frequency to be phi p dot. And this evolves very slowly on timescale 1 over epsilon, which is the radiation reaction time I mentioned earlier. Now we're going to write everything as functions of these two phase space coordinates and epsilon. And then we're going to expand all our functions in powers of epsilon at fixed phase space coordinates. So we're going to do that for the metric, but also for the trajectory. So for the trajectory, it's very simple. So we've got our spatial coordinates. We treat Rp, the orbital radius, as a function of orbital frequency and epsilon. It's always going to be on the equator. And now this phase phi p is still just phi p, unchanged. We're not expanding this or anything. Now we expand everything in powers of epsilon at fixed phase space coordinates, which means in particular, this orbital radius here is going to get expanded out. So we have an R0, which is a function of omega, R1 is a function of omega, etc. So the position in phase space is specified by phi p and omega, because once you know omega, you also know the orbital radius. And the trajectory through phase space is governed by very simple coupled ODEs. So the d phi p dt, I just said by definition, I'm going to call that omega. So omega is just the only thing on the right-hand side here. There's no corrections. And then d omega dt, so the rate of change of the orbital frequency, we're going to expand that at fixed omega in powers of epsilon. And the fact that we're restricting ourselves to quasi-circular orbits means that there's no dependence on phi p over here. We only have slowly changing functions on the right-hand side. Everything only depends on omega. Now, there are other ways you could formulate this whole thing. So one way you might have seen, and in fact, one way that we described in our paper, with my paper with Jeremy Miller, is rather than using omega as a coordinate, we used what we call slow time, epsilon t, as a coordinate. So you can do exactly the same thing, treat everything as a function of phi p, t tilde, epsilon, and then expand everything in powers of epsilon at fixed phi p and at fixed t tilde. Now, the reason we gave up on that, well, partly I think that doing everything in terms of phase space is just prettier, it's more elegant, but much more importantly, it turns out to be way more accurate. An expansion at fixed phi p and omega is way more accurate than an expansion at fixed phi p and t tilde. Also, it simplifies the field equations. The field equations are simpler if you use omega rather than t tilde. So that's what we're going to be using. Now, let's get out of this annotation. Now, that's not quite the full story, because it's not just the orbit that's evolving. The black hole is also evolving. So gravitational waves are falling into the black hole. The black hole is absorbing energy. It's absorbing angular momentum. So the mass of the black hole is actually not our background mass. There's a small correction that's evolving slowly with time as the black hole absorbs radiation. Similarly, you can't actually consistently set the spin to 0 because the black hole absorbs angular momentum in the radiation that falls into it. So we have a small correction. So here delta M and delta J are both order 1. I'm pulling out the factor of epsilon to show the overall scaling. Now the spin is always going to be treated as a perturbation for us. We're always working on a Schwarzschild background. Both of these things, the delta M and the delta J, are going to appear in H1, our first order metric perturbation. They're not going to appear in the background. So we don't just have a slowly evolving frequency, we actually have a set of 3 variables that are slowly evolving: the frequency, the mass of the black hole, and the spin of the black hole. So now rather than just d5 p dt is omega and d omega dt is some series like this, we now have equations for each of the variables. The rates of change of the mass and spin, the leading order terms here, are just the standard energy and angular momentum flux into the black hole, the things that people have been calculating since the 70s. This first term depends only on frequency. At sub-leading orders, you start to actually depend on a full set of parameters. So you depend on delta M and delta J. Now here I've sneakily replaced T with S. And I'm going to start using S as my time for everything. So at the particle, S is just going to be T. But at the horizon, where I might prefer to define delta M and delta J, S is going to be V. So I would time along the horizon and a time along the particle. Now, if I substitute all my expansions into this self-accelerated equation of motion and solve order by order, I get some fairly simple forms for the solutions. I realize now I'm opening the same paper I'd already opened, but I'll do so anyway. So the formulation I'm describing here, unfortunately, is not the formulation that we used in the body of the paper, because I only came up with it right before submitting the paper for publication. So the formulation we're using is in Appendix A. And so, for example, here's the leading order orbital radius as a function of frequency. Here's the correction to the orbital radius as a function of frequency. This U0 is the t component of the forward velocity at 0th order, which is a simple function of frequency. And on top, we have the radial component of the first order self-force, which again is going to be a function of frequency. And then those capital Fs I wrote down are written in terms of the self-force, in terms of frequencies, like this. So fairly simple, compact expressions. So that's just the evolution of what you could call the mechanical parameters, the orbit and the black hole. Now we want to solve the Einstein equations. And what we're going to need to do is define all these parameters, phi p and the slowly evolving things, as functions on space-time. So what we're going to do is foliate our space-time with some slices of constant s. So s is our time coordinate. We're foliating the whole space-time with slices of constant s. And then what we're going to do is just define phi p and ja to be constant on each of these slices. So they only evolve as you move from one slice to the next. Now in the paper with Jeremy, we wrote everything down for kind of a generic choice of s. It can be anything you like. What we use in practice is what I've drawn here, where on the inside, to the left of the orbit, so this is the particle falling in, to the left of the orbit, we use exactly v. So we have v on the horizon. To the right of the orbit, we use exactly u. So it goes out to scribe plus along surfaces of constant u. And then in some region around the particle, we use exactly t. So we find that to be convenient for our purposes. Okay, so expanding the Einstein equation. So the basic idea is, rather than thinking of things as being functions of time s, I'm going to think of everything as a function of phase space, coordinates on phase space. And then once I know the s dependence, the time dependence of the phase space coordinates, that will then give me the time dependence of my full metric. So the idea here is that all of the time dependence in the metric comes entirely from the evolution of the black hole and the evolution of the orbit. Now again, I want to do exactly the same as I did with the orbit itself. I want to expand everything in powers of epsilon, holding fixed the phase space coordinates, and now also holding fixed the spatial coordinates on space-time. So we've got our background metric, which only depends on spatial coordinates. We've got an H1, it depends on spatial coordinates, but also phase space coordinates, same with second order, etc. And now a key assumption in everything is that the solution exhibits the same periodicity as the orbit. What I mean by that is that phi p is intrinsically a periodic coordinate in phase space, and I want my metric perturbations to therefore be periodic in phi p. Now, if each of these guys is periodic in phi p, then I have a discrete Fourier expansion. So I can take each of these perturbations and just expand in a discrete Fourier series. This is not a Fourier series in time. There's no omega t, there's no omega s. It's discrete Fourier series in phi p itself. So that kind of removes the fast time dependence and leaves us with these coefficients that are only functions of slowly changing variables and spatial coordinates. Now again, we're going to use a tensor harmonic expansion. So each of these guys is going to get further expanded in spherical tensor harmonics. So then I've got coefficients that depend on these slowly changing parameters and just Schwarzschild radius coordinate. And then I've got everything else factored out. Now, one important thing to note here is that the dependence on phi here is always e to the im phi. So what we always have here is a function of phi minus phi p. So that's inherited from the stress energy tensor, which is also always a function of phi minus phi p. And that's important because if we then evaluate our metric perturbation on the orbit where phi equals phi p, then everything only depends on slowly evolving parameters, which means in particular our self force, which is constructed from the metric perturbation on the particle. The self force is only going to depend on slowly evolving parameters, frequency and the mass and spin perturbations of the big black hole. There will be no dependence on the fast phase phi p. Okay, so if we have expansions like this and we substitute them into the Einstein equation, what happens? So all the dependence on time is encoded in a dependence on phi p and these evolving parameters. So wherever we have a derivative with respect to time, we apply the chain rule. So we get derivative of phi p with respect to s times a derivative with respect to phi p plus derivative of the parameters with respect to time times a derivative with respect to the parameters. So this acts on these coefficients here. So this term is just the frequency. This term, we already said what it was. It has this expansion in these capital Fs. Now, when we act on individual modes, this phi p derivative just brings down a minus im. It's just acting on this, so it's just bringing down a minus im. We've already got an omega, so now what we have is minus im omega. Then we have plus all these small corrections that are proportional to derivatives with respect to the parameters of the system. So with respect to orbital frequency, with respect to black hole mass, with respect to black hole spin. These two guys are not especially interesting because the perturbations, like the first order perturbations that are proportional to delta M and delta J, are very simple analytical functions, so we can just evaluate these derivatives straightforwardly. This bit is much more interesting, and we're going to have a whole workshop session on this bit. That'll probably be the next session. Well, what I want to emphasize here is that this term, this first term, this minus Im omega, is exactly the same term you would have if rather than this Fourier expansion where you have a phi p, if rather than that you just had an omega s. Now, again, I'll stress phi p is not equal to omega s. But when you plug it into the Einstein equation, what comes down from that phi p derivative is the same, leading orders, the term with no epsilons next to it, is the same as if we were using an omega s here, which means it's the same as if you put in a geodesic particle moving on a circular orbit. And then all the differences, everything that is different from that, is all pushed into higher order corrections, all these order epsilon corrections. Okay, now I'm realizing that I'm not going to be able to finish everything I wanted to talk about before handing it over to Barry. So I'm going to just cover this slide, then hand it over to Barry, and then I'll finish up the last bits here after Barry has finished his more hands-on section. So this is the structure of the Einstein equations we're trying to solve in the multi-scale expansion. But first, I'm going to just hop back to what it looked like in an ordinary Taylor series. So we have a linear operator on the left-hand side. These are all, covariant four-dimensional things, stress energy tensors, and then this quadratic term. And the quadratic term is what we're going to be focusing on for the rest of the workshop. So what happens to that quadratic term and what happens to this equation overall? So we've done two things now. We have decomposed into spherical harmonics. More than two things. We've decomposed into spherical harmonics. We've substituted this ansatz for the metric with this very particular dependence on the phase space of the system or on the time dependence of the system, whichever way you like to think of it. And we've put in these expansions for the rates of change of the parameters like this. So what comes out of all of this? Well, we're going to do one more thing. We're going to specialize to the Lorentz gauge. So all of our second order calculations to date have been in the Lorentz gauge. So the Lorentz gauge, if you're not familiar with it, is just that the divergence of the trace reversal of the metric perturbation is 0. Now, here we're using a particular form of the Lorentz gauge. We're not saying, the 0th order derivative, meaning 0th order in the 2 timescale expansion derivative. We're not saying that when that acts on H2, we get 0, and when it acts on H1, we get 0. What we're saying is you add up all the perturbations, take a total divergence of all the perturbations, the sum, set that to 0. And really, I should be including all the higher order terms here. It's the full sum we're setting to 0. And so then in the 2 timescale limit, or in the multi-scale expansion, you get a sequence of equations. You get a gauge condition for H1 by itself. You get a gauge condition for H2 that involves H1, etc. So that's just a technical detail. You can think of it as we're just in the Lorentz gauge. Okay, so when we substitute our multi-scale expansion and we substitute our spherical harmonic expansion, everything reduces down to radial ODEs, like it would do in the familiar setting of just geodesic particle on a circular orbit. Everything, in that case, you would have a discrete time frequency spectrum, and you would get down to radial ODEs, like I mentioned earlier on. So here we have radial ODEs again. And the left-hand side here is exactly the same as it would be in the frequency domain. So the genuine time, coordinate time frequency, not phi p. The left-hand side is identical to what it would be in the frequency domain if you put in a perturbation like this, with a e to the minus im omega s, where s is your time. So this piece here is basically second radial derivatives plus frequency squared. And then this piece here is first order radial derivatives, and it also couples between the different tensor harmonic modes. But again, these are equations that have been standard in the literature, or this left-hand side has been standard in the literature for quite a long time. You can look up the form of this again in my paper with Jeremy for a generic choice of time s. And yeah, it's simple and familiar. What's on the right-hand side is more interesting. Okay, so the leading term here looks just like it would if you had a particle on a circular orbit, circular geodesic. You have a radial delta function coming from the stress energy tensor times some coefficient that's a function of orbital frequency. The second order stress energy term will have a delta and a delta prime. I'm not going to talk about that. You have this quadratic term, which is now a mode, a spherical harmonic mode decomposition of these quadratic products of derivatives of H1. Then we also have one more term, a term that didn't appear in the ordinary perturbation theory at all. So what this term is, it's the piece that comes from these order epsilon corrections. So it's the piece that was proportional to the rate of change of the frequency, or the rate of change of the black hole mass. So because that comes with a factor of epsilon, that never appears on the left-hand side, it appears on the right-hand side. So it's now acting as a source. The slow evolution of the system is acting as a source for the second order metric perturbation. And each of these terms is proportional to a derivative of the first order modes with respect to orbital frequency or with respect to black hole mass or black hole spin. Okay, so I think because Barry has to leave in about half an hour, I'm now going to hand it over to Barry. So what Barry is going to do is give you a concrete tool to calculate this term here, this quadratic term, taking input modes from the solution to the first order equation. So it generates a whole list of first order modes in the Lorentz gauge and outputs a mode of the second order Einstein tensor. Okay, and then once Barry's finished guiding you through that, we can hop back to my last few slides. Okay, Barry, take it away.
Thanks, Adam. Let me just share my screen. Niels and Adam are here, so if you have questions, certainly feel free to ask either on the chat or probably on the chat is easiest. So Niels or Adam would be people to message. Okay, so I'm going to lead you through a kind of a hands-on tutorial on how we actually use a code that we've released for generating that right-hand side, the source for the second order field equations. And that code has been released as part of the Black Hole Perturbation Toolkit. So at the CAPRA meeting a couple of weeks ago, we released a couple of codes to solve the Lorentz gauge equations and to do the mode coupling. There's now a third repository which puts it all together to actually compute that source. So I've put a link in the chat to this page here for the second order Schwarzschild repository on the Black Hole Perturbation Toolkit. So it's github.com/Black Hole Perturbation Toolkit/second order Schwarzschild. It should be publicly available. and you should be able to actually check it out. So for the tutorial, I'm actually going to download this, compile everything, show you how to compile it, show you how to run it, and then how to work with the output. Okay, so the first step, I'll come back to explain what's in here in a few minutes. The first step is to actually get the code. So if we go to this page, we can just click on the green button here, copy this link in here, like that, and then download it using Git, using whatever Git tool you prefer. For the purposes of the tutorial, I'm actually going to do this on the command line. So I'm going to switch over to a command line terminal and run that command. So I run git clone and then the URL from the web page. And when I do that, it will download it. It's about a megabyte or two, or 3 megabytes possibly. Should download fairly quickly. And then you'll have a directory called second order short chilled, which we can go into. And if we type ls there, you'll see the same files as were shown on the web page. Now I'll come back to this in a minute, but I think first I will just do a quick tour of exactly what's included in that repository. So let me go back to the web page here. And if we look at the files that are included, there is a README file here, which gives an explanation. In fact, the contents are down below, gives a very brief explanation of how to compile the codes and how to run them. Then there are 3 primary code directories in here. One is this H1 Lorentz. So this is actually from a separate repository that was released a couple of weeks ago. This solves the first order linearized Einstein equations in Lorentz gauge with a point particle source. So it's the C++ code, and that can be run to generate the first order metric perturbation data, H1. There's a second one, kind of a related repository here called First Order Mathematica. And that's a little bit of a hack because this H1 Lorentz code, as it is currently, doesn't compute the static modes in the even sector. So when L and M are an even integer and the frequency is 0, this code doesn't currently work. So we have a separate Mathematica code for doing that. So in effect, whenever M is 0 and L is an even number, this code gets run, and otherwise this code below gets run. The one above is written in Mathematica. There's some difficulty with evaluating these things accurately, although in principle it could be distilled down into C code as well. The third directory we have is this second order Ricci directory. So again, this is a separate repository which you can download, but it's also included in here. And this is the thing that takes in output from H1 Lorentz, sticks it into the mode coupling formula for the second order source, the right-hand side of the second order field equations involving H1 squared, and then returns the result. So those are the main drivers of this. Then the only other thing we have is a couple of scripts in here which make it easier to run the above 3 codes. Okay, so in particular, there's this generate source.py, a simple Python script that runs everything in the right sequence with the right parameters and arguments to take basically an input and R naught value for the radius of the circular orbit and spit out the result. Okay, if we go into, well, the README first, you can see it just gives a, as I said before, it gives a fairly short explanation how to run the code. Probably more technical are these 2 H1 Lorentz and second order Ricci codes. So if we go into each of these in turn, okay, in the H1 Lorentz, you'll see that it has its own README file with an explanation of the code, which is based on work that was done in this paper by Niels Warburton and Starp. There's an explanation of what you need to have pre-installed. So they're fairly common standard libraries that you need to be able to run this code. So the GSL, GONS for compiling, and OpenMPI for parallelism. To compile it, you run this command scons in the directory, and then there's an example of how you actually run it. We don't actually need to do this because our wrapper script will take care of that. There's also an explanation of the output and some related papers worth checking out. And if you dig down into here, you'll actually see the C++ or C source files included. So if anyone has any questions about this, Neil is on the call and he's happy to answer them at the end. So in addition to the H1 Lorentz, we have the second C++ code, the Ricci code for doing the mode coupling. Again, this is a C++ code. There is a README file telling you exactly what you need to have installed. So again, they're fairly standard, fairly common standard libraries, the GSL, HDF5 for input and output, a reasonably modern compiler, the Boost library, and scans again. And to build this, you just run scans. So I'll show you that in practice now in a second. Okay, and that's pretty much the structure of this repository. We don't really need to worry about the details of these files, of these codes, other than knowing what they do, because all we're going to worry about is compiling them and then running this high-level script. So let me now switch back to my terminal, and I'll show you actually how all that works. Okay, so we're back in the terminal where I've downloaded the repository. We have all those directories, the first order Mathematica, the Ricci and Lorentz. What we need to do first is compile these two codes here, the Ricci and Lorentz one. So let's go into H1 Lorentz first. And all I need to do to compile that is run scans. Now I have several CPU cores on my laptop, so I'll actually run this with 8 parallel compile things just so it runs a bit faster. This will go off, it will compile everything, and it will hopefully finish. If you get this bluey purpley line saying linking H1 Lorentz, it's probably worked. If I type /H1 Lorentz and it runs and tells me how to use it, then that means I've compiled it correctly. If there are any problems, it's most likely that you don't have one of the required libraries installed and you need to install that using whatever is the standard way on your system. We'll now go back to the Ricci code and compile that as well. In this case, I actually need to edit some of the compile options because this code is set up to compile perfectly on Ubuntu. I'm on a Mac, so I need to change something slightly. So I'm going to edit the source / scanscript file, which is the scans file that tells the system all about how to compile my code. In particular, there are these environments that are useful to be set depending on what your system is. So if you have libraries in specific locations, you can tell them locations here. If you have include files and locations, you can say it here. If you specific compiler flags, you can put them in here. In my case, my compiler isn't called G++, it's G++ -13. So I'm going to make that one change, and exit out, and I'm going to run scans again. Okay, this one takes a little bit longer to run. It's a C++ code that uses Boost, so just the actual compiling part takes on the order of 30 seconds to a minute. So let's just leave that running. And see how it goes. It's going to compile. So there are separate files for each of the 10 components of the second order Ricci tensor. It's a symmetric tensor with 10 components. And then there are some other bits to it as well. But the really big ones are those 10 files. So let's just leave that running for a second, and I'll take this moment to switch back just to explain exactly what's being compiled. I'll come back to the compiler again in a second. So right now, the second order Ricci code is being compiled. And if we look in here, the most important bit of this directory is in the source part, which has all the source files. There are 10 files here. R2 means second order Ricci, and there are numbers from 1 to 10, representing the 10 components of the metric in the Barak-Lusso-Sago basis. And then there are some extra things for loading the first order metric perturbation and some wrapper jewels and things like that. If you click into each one of these files, essentially the bit that's taking a long time to compile are these lines here. If I scroll to the right, well, I'd actually have to scroll to the right for quite a long time. These are quite long expressions implementing the coupling formulas that Adam talked about. So this is the meat of this code. It's just these two lines here and special cases for specific values of L. Okay. I think we're just done with compiling. So let me switch back again to my terminal. You can see that the compile finished. It said it's linking. There are 3 executables linked in here. Reachy is the main one. So if I try to run that and it gives me a usage message, that means it's worked. There are 2 other ones, the S and the M. And these are contributions to the second order Reachy from the perturbation to the mass and the spin black hole. So these are extra small effects that we can include, although the main thing to worry about is this Reachy here. So again, there's a usage message. So what you do here is you run this code, you give it a directory for the input. So these are the first order metric perturbation fields and in the format I put it by H1 Lorentz. You can actually have 2 different first order fields if you want. So you can have the second directory. There is a L max. This is how many second order L modes to output. And then there's a delta L max, which says how many first order L modes to use in coupling, the coupling formula, in order to produce the output. So we could run this like this, but again, as I said, what we're actually going to do is go up 1 level higher and have a look in here and work with this file generate source.py. So if I just run that, it will tell me what I need to give it. I need to give it an R0 value. That's the radius of the circular orbit. How many first order retarded mode L modes to include, and how many second order modes to output. So I'm going to try running this for, say, a radius of 10. I'm only going to do 6 first order modes just in the interest of running quickly. And I'm only going to output up to L equals 2 in the actual output for the Reachy tensor. If I run this, it will go off and do a sequence of things. It will first generate a grid. It will then run, this is running the H1 Lorentz code, which runs quite quickly. There's modes up to L equals 6 done. Next up, it will try to evaluate the even static modes. So that uses the Mathematica code for M equals 0, L even. And you can see that basically the numbers here, 2, 4, and 6 are the L values. It's going to need the field and its first and second derivative on a grid of radial points. So this is going to take a couple of minutes to run. And each time it computes something, it will print the output. So this is I equals 1. So the I equals 1 component of the metric perturbation. For L equals 2, M equals 0. And H just means not differentiated. So we'll see this will go up to I equals 7, up to L equals 6. And then it will compute the first derivative and the second derivative. Okay, so I'm going to leave that running for a minute. And I will just once more switch back to the web browser. And what I want to do now is actually lead you through, by looking at this Python file, exactly what that script is doing. It's a fairly short file. It's only about 50 lines long. And it just, it runs all the commands you've just generated. Okay, so it starts out, takes these 3 arguments: the radius of the orbit, the number of first order fields to include, and the number of second order fields to output. So those are the arguments of this function, this program. There are some setups here for creating all of the directories where all the data will be stored. So the radial grid will be stored in this directory here. The first order, the output of H1 Lorentz, right, will go in this directory here. The output, the H1 Lorentz output is actually processed into a slightly different format and output to this directory. The even static modes are output to this directory, and the Reachy tensor, the data itself, will be output to this directory. We then create all the directories and then start running each of the codes. So there are 5 steps here. First off, create a radial grid. So this sets up which values of R the Ricci tensor will be evaluated on, so on a grid of radial points. And there's again a Mathematica notebook that actually generates this grid currently. So it runs this Mathematica notebook. And if you look into this notebook, you can see actually how the grid gets set up. We've tuned it to be reasonably accurate for the calculation we're looking at. Once the radial grid is set up, we then run the Lorentz code, H1 Lorentz. This is run with NPI with as many CPUs as you have on your computer. So it will run faster on a HPC machine than it will on a laptop. That generates the first order metric perturbation data. We then run the static mode code using Mathematica. So it actually runs this file here, which generates the solutions for the even static modes analytically, and then evaluates them numerically on a grid. We then run a code which processes everything from the format of all the output and puts it all together ready to be used in the Ricci code. And then last but not least, the actual Ricci code itself runs. And we're running the script to do the mode coupling that takes a R0 value and a number of output modes to include. Okay, and that's all there is to the script. If I go back now one last time to my terminal, you can see that it's still running. So rather than waiting around for it, what we will do is switch over to one I prepared earlier. So you can see that it's got about halfway through computing the static modes. It will finish in another couple of minutes, but let's not wait for it. Let's switch over to one I prepared earlier. Okay, so this is one I prepared earlier, having run the code that I just described. And what you get is you get an extra directory here called data. If you look in that data directory, there are three things. There's the grid, which just has a HDF5 file with the radial grid points on it. You have a H1 directory, which has a subdirectory for the given radius of the orbit. And then in there are three things. There's the retarded field data, the static modes, and then the unprocessed retarded field data. If we look in H1 ret, you'll see that there are actually a whole set of files here, data files in HDF5 format for L up to from 0 up to 6 and M equals 6. So that's the H1 directory. Just to remind you, that's H1. We've done grids. The last thing is this D2R directory. Oops. Again, there's a subdirectory for the given orbital radius, R0 is 10. And then for the fact that we are computing the Ricci tensor constructed from H1 ret times H1 ret, the retarded field. And we're seeing here that there are actually three files, a source for the actual secondary metric perturbation, and then pieces from the perturbations to the mass and the spin. This HDF5 file here, source.h5, is the main output of this whole code. If I use the h5ls command to list what's in there, you'll see that there are a whole load of data sets. There's one which contains the grid, so the radial grid. It's a grid with 6,382 points in this case. And then there are a whole load of data sets, one for each value of I, L, and M. So L and M are the spherical harmonic modes, and I goes from 1 to 10. It's the component of the Ricci tensor. Okay, and last but not least, if you want to, you can actually just look at this data itself if you want, but probably easier is if you look in the second order Ricci directory and then notebooks, there's a notebook called load second order Ricci data. So it's the Mathematica notebook. If we open that, and I'll switch over to the one that's been opened. There's a very short notebook here which shows you exactly how you can load that data into Mathematica. Oops. Oops. Start with a clean kernel. Oops. So I need to change this R naught value to 10.0. Okay, I need to tell it where the data is. It's not on Google Drive, it's in this directory here, second order short shield /data /d2r/r010/d2r retret. So that's where it is on my computer. It may be in a different location on yours. Let me make this slightly bigger. That's easier to see. Okay, so you may need to change this line to tell it wherever your output is on your own computer. If we run that, then we can load the radial grid, so the grid of R values. There's a fairly simple function here which uses import to import the data sets for a given I, L, and M. And then we'll actually run that function for L equals 2, M equals 2, all I from 1 to 7. Those are the only ones that are non-zero for the even sector. And L and M and L plus M is even. Okay. We can then actually plot that thing. And this is the sort of thing that you get. So on the x-axis here, we have R minus 2m, so the distance from the horizon on logarithmic scale. And on the y-axis, we have the actual Ricci tensor for that given I equals 1, L equals 2, M equals 2 mode. And we have the real part in, the real part of I equals 1 in blue and the real part of I equals 7 in orange yellow. And you can see three features here. One is over towards the right, so towards infinity, it's decaying. Over towards the left, it is heading towards more or less a constant, although there's some oscillations. And then around the middle here, near R equals 10, it's going upwards, although it is finite. Okay, so in principle, we could take this, and this would be now the source to Lorentz gauge equations at second order, use the standard variation of parameters method to integrate homogeneous solutions against this source. There are some problems with this, which we'll have to come back to in future tutorials. So one is over to the right here, another is over to the left, and then a third is towards the middle. That if these things don't fall off fast enough, and in fact, the thing in the middle isn't even finite, then we won't get a finite integral. Now, it turns out that because we're only coupling a finite number of first order modes to get to the second order mode, this thing in the middle is actually finite, although it does look somewhat cuspy. So let me show you that by zooming in that region. So if I zoom in the region of, between R equals 4 and R equals 14, and get rid of the log scale, we can see how it behaves. Get rid of the absolute value as well here. Oops. Okay. So this is the sort of behavior we have for this second order Ricci tensor close to the world line. You can see that it sort of looks like it's diverging, although it's actually finite. If we were to add more modes from first order metric perturbation, this would go upwards and upwards and upwards, and eventually it would tend towards a logarithmic divergence or a divergence. Anyway, a 1 over delta r squared divergence, where delta r is the distance from in here. This is r minus 2m is 8. Okay, the last thing in this notebook is that you can see that there are all these oscillations over to the right and to the left. That's related to the fact that we're plotting this on a constant t slice. We could equivalently plot it on a constant u or v slice. And it's actually fairly simple to transform that. We just multiply by this exponential. And then if we plot things, we see that a lot of the oscillations go away and we get something much smoother. Okay, so I think we're almost done. Let me finish up by switching back one last time to the terminal, just to show you that it did in fact finish. So you can see if I scroll back a little bit, I'd finished running all of these static modes calculations, which in this particular case is the slowest part, although it could easily be optimized. We then have a section where Mathematica is run one more time to process all the data into a single set of files, so the static modes and the non-static modes together in a common format. And then finally, the actual coupling code itself is run. So that will load two sets of data, one for each H1 that goes into the coupling formula. In this case, it's the same twice. You can see it uses OpenMP for parallelism, so it runs on 8 threads on my laptop. And in this case, there are 29 ILM modes to compute for I up to L equals 2. It also runs the Ricci code 2 more times for the M and the S parts. That runs pretty quickly. If we then look at our data directory, it's in the exact same format as the one I prepared earlier. And in particular, we have that source file in there. Okay, so that was a fairly quick tour through the code. What we'd like to do is have you guys actually try it out. So feel free to try and follow those steps. All you really need to do, if you can't remember what I said, is go to the link in the chat that I posted and compile the two codes as explained in their README files, and then run the high-level Python script. And if there are any problems, Niels Warburton is here and is happy to try and help debug people's individual issues. But for now, I think perfect time for me to hand back to Adam, who will maybe go into a little bit more detail about those problems with the various divergences.
Thanks, Barry. I think I actually will not discuss those problems. I can briefly mention them. So yeah, while you're all hopefully working away on downloading and running the code, I will quickly go over a few last points. So again, what Barry was just guiding you through was a calculation of this particular piece. And what he mentioned as well, which is important, is that when he summed up a finite number of first-order modes, he was getting a finite result for D2G. So the output from the code is the Ricci tensor, not the Einstein tensor, but you just do a trivial trace reversal at the level of ILM modes, and you'll get the Einstein tensor. So yeah, you get a finite result for each mode when you're summing up a finite number of first-order modes. That's because each of these first-order modes is always finite at the particle. The modes are finite. Of course, the four-dimensional field is singular. And what Barry also mentioned is when you keep adding up more and more first-order modes, this keeps getting bigger and bigger and bigger at the particle until if you add up an infinite number of first-order modes, this second-order source diverges like 1 over delta r squared. So the output of that coupling code, that second-order Ricci code, is not accurate in a vicinity around the particle because it's trying to reproduce something that's infinite by adding up a whole bunch of finite things. And we'll never get enough first-order modes to accurately reproduce that singularity. So when you're playing around with that tool, keep in mind the purpose of that tool is to capture things kind of at a significant distance from the particle. In practice, we find if we use 40 or 50, L equals up to 40 or 50 first-order modes, that we get a good representation of the modes of the second-order Einstein tensor at a distance at least, say, 2m away from the particle, a radial distance of 2m away from the particle. We get good accuracy using that. We'll have a whole separate session later on how to calculate this accurately in the vicinity of the particle. Okay, so these equations I've written here are actually not the form of the equations that we use, because as I mentioned, we never actually use this second order stress energy tensor. What we use instead is a puncture scheme. So at the particle's position, the first and second order metric perturbations diverge. This should not be an M2, this is just an M. The first order perturbation diverges basically like a Coulomb potential. It's the mass of the particle divided by distance from the position of the particle. And the second order, it's the square of that. It's 1 over distance squared, so a stronger divergence. At third order, it would be 1 over distance cubed, etc. So the way we work in practice is we get a local representation of the metric perturbations using method of matched asymptotic expansions. We get a local expansion for H1 and H2 around the particle's position in 4 dimensions. Those are given in covariant form in this paper here. Then, rather than solving for the retarded field, H1 and H2, what we do is we construct these puncture fields, which are just capturing the local singularity. We subtract off the puncture field from the physical retarded field, and we make our numerical variable the residual field, the difference between the physical field and the puncture. So we're removing as much of the singularity as we can using this puncture. Another way to think about this is it's a kind of a broader idea of a particle, even when you don't have a well-defined distributional point particle source. You can just think of throwing away your extended body, taking your fields that were outside the body, extending them down to some representative world line, and they will diverge at the particle's representative world line. And those are the punctures in the geometry. So we formulate field equations for the residual field. What that means is we just move the puncture to the right-hand side. So now we have a linearized equation for residual field with sources on the right. Here I've written this in a form where we don't have T1 and T2. There's a bit of a subtlety in how you interpret derivatives in these operators. The idea here is we are starting with a vacuum equation away from the particle. We're then evaluating all these derivatives, and then we're extending this source, the total source, down to the particle's position. And when you do that, you never need to involve the delta function sources. So this is a very general method, developed in any space-time and any coordinates, whatever you like. And the idea is, because you've subtracted off the puncture, your effective source, the source on the right-hand side, your thing that's sourcing the residual field has some degree of regularity. It's maybe continuous or Cn at the particle's position. Now we, of course, are working at the level of modes. So if we go back to our multi-scale equations, taking these equations, we can just throw away this T2. We can work with the residual field at first order as well. In practice, the code that calculates the first order metric perturbation that Barry showed you, the code written by Niels, that doesn't use a puncture scheme at first order, that solves directly this equation with a delta function source. But at second order, we just throw away T2. We move the puncture to the right-hand side, and we're left with residual field modes at the left-hand side. So this is our puncture on the right-hand side. This is still the same quadratic source that Barry showed you how we calculate. And this is the piece of the source that comes from the slow evolution of the first order field. So these are the equations that we solve in practice. And over the next few workshop sessions, we will go through piece by piece. So we've covered the calculation of this at a sufficient distance from the particle using first order modes. I think in the next session, Leanne and Niels will cover the calculation of this source. And a little bit further down the road, we will cover the calculation of the source near the particle, which involves the puncture, and it involves a very special way of calculating this quadratic piece. So that's what's looking ahead. As I mentioned, we also ultimately end up introducing punctures at the boundaries, so at large R and at the horizon. So that's to deal with other problems that we'll describe later. So this puncture isn't necessarily just the particle. We have punctures all over the place. We're subtracting off singularities left and right. Okay, so I'll just wrap up this portion on the multi-scale expansion with a reminder of the big goal, which is waveform generation. And the waveform generation that comes out of the multi-scale expansion ultimately is very, very simple. So this is a given LM mode of H plus or H cross at infinity. So we have amplitudes that are functions of our slowly evolving system parameters, the orbital frequency and the mass and spin of the black hole. The first order perturbation only depends on the frequency. The wavy part of the first order perturbation only depends on the frequency. And the second order perturbation will then involve the mass and spin of the big black hole, the corrections to the mass and spin of the big black hole. So these H1s and H2s are just the output of solving the first order Einstein equation and the second order Einstein equation evaluated at infinity. It's just a direct output of the calculation you've done. And then outside, we've got this phase factor with the phi p dependence. So the idea is, because when we look back at these equations, because derivatives with respect to orbital frequency, for example, never appear on the left-hand side, they only appear on the right-hand side. What that means is you can solve this equation for a given value of frequency, solve it again for another value of frequency, keep doing that again and again for all the values of frequency you're interested in. An equivalent way of saying that is all the values of orbital radius you're interested in. And then you just store these amplitudes, these slowly changing amplitudes at infinity. Also, as you're doing your calculation, as you're solving the field equations, you also calculate these driving forces that come from the first order self force, or it comes from fluxes, or it comes from whatever. We'll discuss a bit more about that in a later session. So you pre-compute these amplitudes, you pre-compute these driving forces. You've then got this as a function of omega, mass and spin of the black hole, and phi p. You've got very simple ODEs, a very simple set of coupled ODEs to find out how omega depends on time at Scri plus, how phi p depends on time at Scri plus, and how the mass and spin of the black hole depend on time at Scri plus. So all you're doing is you have pre-computed all of this. You then just zip through the parameter space to calculate phi p as a function of s, and these JAs as a function of s, and there's your waveform, done. So that's why this method is so fast. And of course, for anyone who's done adiabatic calculations, you can now do simple adiabatic calculations in a few minutes, starting from scratch, basically. This will look very familiar. All of this is, building on long development of adiabatic methods of generating waveforms. It's all based on pre-computing things as functions of slowly evolving parameters, and then just solve very simple ODEs to generate your waveform. And actually, this particular form, where we've got these slowly evolving parameters, when I was formulating it this way, I was actually particularly inspired by EOB. So EOB people can credit themselves with that. Okay, now the last thing I want to go through in the last few minutes is just talk about how the derivation works for the code that Barry showed you. So Barry showed you really long formulas, you scroll through them for ages, that are giving you modes of the second order Ricci or Einstein tensor constructed from sums of first order modes. So these are couplings between first order modes, and the output is modes of the second order field, or sorry, the second order source. So as we mentioned, we are using a particular basis of tensor harmonics, the Brach-Lustow-Sago harmonics, written like this. So we use that when we solve the field equations, and we put the source in those mode in that basis. Let me actually show you what these look like, because there's lots of different harmonics people use, and not everyone will be familiar with this particular basis. So this is again the same paper by myself and Jeremy Miller, but you can find formulas for this basis all over the place, in particular in the papers by Brach and Lustow and Sago themselves. So each one of these harmonics is a matrix in TR coordinates, or in whatever coordinates you like, but this particular form of writing them out is in TR coordinates. So this is just a matrix of components, and you have one matrix for each value of the I. So this is I equals 1, and you can see it's in the TT component and the RR component, and then outside is just an ordinary scalar spherical harmonic. Y2 is in the TR component, Y3 is a different combination of TT and RR. Then the 4 and 5 involve derivatives of scalar harmonics. The 7 involves more complicated derivatives of scalar harmonics, etc. So this is just a complete basis of tensor spherical harmonics that separate the linearized Einstein operator. So let me hop back to slides. So we use this basis to solve the equations, and we put the source in this basis, but actually to derive the formula, that is not the basis that we use in intermediate steps. Another basis that I actually used in deriving those formulas is the Martel-Poisson basis, which is more like, it's a bit more traditional. It's more like the basis used by Reggie and Wheeler originally. All of these are basically equivalent to each other, but just slightly more convenient for different purposes. So in this basis, first off, we split everything into a TR plane, or in this case, an SR plane, and S2, the just unit sphere. We could use any coordinates we like on this plane. We can use any coordinates we like on the sphere, but these are the particular coordinates we're using, SR theta phi. So in this decomposition, where lowercase indices denote things on TR plane and uppercase denote things on the sphere, the background metric splits into a nice product metric. We have a metric on the TR plane, and we have a separate metric on the sphere. Omega AB here is the metric on the unit 2 sphere. And then there's just this overall factor of R squared. So then in this decomposition, take any given symmetric rank 2 tensor. So this could be H1, it could be H2, it could be whatever. We expand it out like this. This is a notation that you will find in the recent paper that we put out on the derivations of these coupling formulas and on perturbation theory, a second order in Schwarzschild in general. So things on the TR plane, we just expand in spherical harmonics, ordinary scalar spherical. Things that are mixed, TR plane and S2, we expand these in what are called vector harmonics. So we have an even parity vector harmonic where I'll put a plus, and an odd parity where I'll put a minus. Then things that are entirely on the 2 sphere, so the tensor components are on the 2 sphere, we have a piece that's proportional to the trace There's a typo here. There should be a capital omega AB. So a piece that's proportional to the unit two-sphere metric. So that's the trace piece of this. And that's just a scalar. So that gets a scalar harmonic. Then we have a piece that's even parity, tensor harmonic, rank 2 tensor harmonic, odd parity, rank 2 tensor harmonic. So I'm just putting pluses everywhere there's a even parity and minuses everywhere there's a odd parity. Now it turns out to be even more useful to use spin-weighted harmonics as intermediate steps. And in fact, when my student Andrew Spires reproduced all the formulas, all the coupling formulas, he actually used these start to finish and then just transformed the results into whatever basis you like. So as a quick example of how you do this kind of decomposition, let's say we've got a scalar quantity that's quadratic in H, so just H contracted with H. We expand out into this 2 plus 2 kind of formulation where we have things on the TR plane and components on the sphere. So we get TR plane contracted with itself, we get mixed contracted, and we get things on S2 contracted. We then substitute the expansions of each of these things. So this guy gets expanded in scalar harmonics. This guy gets expanded in scalar harmonics. These get expanded in vector harmonics. Here I'm just showing you a particular product that appears there. So this is the even parity times even parity vector harmonics. So here we have a double sum. And we'll get a whole bunch more terms from odd parity times odd parity, even times odd, etc. And this piece here as well. Now, in the derivation that I originally did that went into the coupling code that Barry showed you, what I did was express each of these things in spin-weighted harmonics. And I'll show you why that's nice and simple in a second. So all of these harmonics are very closely related. Spin-weighted harmonics are very closely related to vector and tensor harmonics. And this particular contraction here is just a very simple combination of spin weight plus and minus 1 harmonics. So we get this big sum of products of modes with all these spin-weighted harmonics here. Now we want to decompose this quantity into modes. So we take this whole quantity and integrate against another harmonic. So in this particular example, this is just a scalar. So we integrate against a scalar harmonic. And so what we end up with is integrals of products of 3 spin-weighted harmonics. So this is a spin weight 0 harmonic. So we have products of 3 scalar harmonics here. We'll have a product of spin weight 0, spin weight minus 1, spin weight plus 1, etc. And this is very convenient because there's a very simple formula for the integral of 3 spin-weighted harmonics in terms of 3 J symbols. So this is all, traditional stuff that you know from coupling of angular momentum in quantum mechanics. We have the same kind of conservation laws as well that comes from these 3 J symbols. So for example, m prime plus m double prime has to equal m. So if we put in 2 first-order modes, the sum of their m values has to equal the m value of the output mode. Similarly, the spins have to add up correctly. And you have a triangle inequality between the 3 values of L, between L, L prime, and L double prime. So this thing that Barry showed you how we calculate is a sum of terms of this form. This coefficient, which is just 3 J symbols, times first order mode and another first order mode, and you're summing over all of these modes, and you can have a 0th radial derivative or first or second, and similarly 0th or first or second derivative. Okay, so before wrapping up and handing you back to Barry and or Niels, let me quickly hop over to the black hole perturbation toolkit. So the C++ code that Barry gave you a tour of, that is hard-coded to quasi-circular orbits It's hard-coded to Lorentz gauge. It's hard-coded to Bragg-Lusto-Sego harmonics. We have also provided this package written by my student Andrew Spires, or former student. So this package, which you can install just by clicking this button, it's a Mathematica package. This package allows you to have all those same formulas that go into the C++ code, but with any choice of basis you like, any choice of harmonics you like, any choice of gauge you like. It's totally general, and it comes with different options. So we don't have time to go through that today, but I encourage you to download this. So this is if you want to build your own code in different gauge or in a different basis. This gives you the tools you need to do that. And in particular, this isn't restricted to self-force. This could be any second order perturbation calculation you might be interested in. Okay, so we might give you more of a tour of this in the near future. Possibly, we'll see. Okay, so I'm going to hand it back to Barry and or Niels. I think Barry might have left now.
I'm still here, although I might let Niels take it for a minute.
Okay, okay. Over to you, Niels.
Sure. I mean, I have nothing specific to show people, and we've been here for almost 2 hours, so those of you who want to leave should feel free. If anyone has any specific questions about the code, I'm happy to answer that. I could show a little bit more about the H1 code if anyone's interested. So as Barry said, that computes the first order metric perturbation in the Lorentz gauge everywhere in the spacetime. And just as Barry showed for the second order Ricci code, there is also a notebook there for loading that data. So it'll load the metric perturbation, and you can see it. So I could show that if anyone's interested. Otherwise, what I would say is if you have an issue now, we can compiling or running the code, we can talk about it. But if you're not doing it now, or you want to look later, and you do run into a problem, the best way of contacting us about it or dealing with it, rather than sending us individually an email, is to open an issue on the issue tracker on GitHub. So if you're not familiar with that, let me just show you. The reason for that is if you're having a problem running the code, probably not the only one. And other people can see that and learn how to fix it, and it can also tell us that maybe we've done something that works on our machines but doesn't work on yours, and we can make it work more broadly. Okay, I see someone's asking for an overview of the H1 code, so I'll do that in a moment. But just to highlight that point, if you are running into problems, so each repository in GitHub, so here's the second order Schwarzschild repository that Barry was showing that contains these two pieces. There is an issues tracker. And so if you run into something and you had to go at trying to fix it and you can't work it out, just open a new issue. It might be something very minor, which we can quickly reply to and close. It could be something much more significant, and it takes some work to fix. But it's really useful if you just let us know that way, basically. Yeah, so I strongly encourage that as well, rather than sending us individual emails. At the same, that really is good just to do it in the open. We're not going to be annoyed if you find a bug in our code. In fact, it's very useful if you do find one. Okay, so for the H1 code, an overview. I guess I'll start with the output of the code. So in that repository, actually, let me just share that again. Back to the code. So there's this subfolder H1. Just as Barry showed in the second order Ricci subfolder, that in here in H1 there's also a simple set of notebooks. These two are a grid, and this is a script version of this notebook. These create the radial grid. So in order to run the code, you have to first run this notebook. So I can show you that. And then you run the code, and then this notebook will load the data from the HDF5 files that's in some funny structure for historical reasons, but that kind of should make it clear what the structure of the file is, basically. So for instance, the basis from I equals 1 to 10 is not in the order 1 to 10 for historical reasons. So that kind of corrects that for you. Okay, so I mean, I can go through those steps as an individual code, basically. So let me see. Let's open the radial grid notebook. Okay, so this is, if you open that notebook in the notebook subfolder of H1, you'll see something like this. You can see very much this is a working notebook we use. There's some old code that's been deprecated that we use for some historic grids we used when we first tried to do the calculation. As Barry said, we sort of slightly optimized the grids. And so if you run this notebook, it will produce that grid. You can pick whatever grid you want. If you want more dense values, just add more radial points. They're defined in these various regions. So T region, as Adam was showing, there's a region around the particle, and there's a region on V slicing near the horizon and a region on U slicing. And we slowly decrease the density of points in these regions because you want to use as few points as you can get away with just for computational reasons. One thing to note is that many of our packages use this simulation tools package written by Barry and Ian. If you go to simulationtools.org, you'll be able to download that, which is very useful for manipulating basically time series of data. Personally, I find it much nicer than Mathematica's inbuilt commands. So you can just run this and may as well just do this. I think it should work. Just evaluate the whole notebook. In this case, we've got an R naught of 7, and it will just produce a grid. And in fact, it does a few checks by integrating some test function over that grid, just using some basic sort of integrating functions, and then outputs that grid. So here it's created radial grid R7 in the H1 Lorentz input folder. Okay. So yeah, easiest thing to do, just if you're just starting out, just playing with, just pick an R naught value, whatever value of R naught you're interested in, as long as it's outside the light ring, I think it should work. Although you'll probably find it gets funny as you get very close to the light ring, but maybe more sensibly keep it outside the ISCO. So say 6 and above. And I would say as well, the code, works by numerical integration. So it sets some boundary conditions at some large radius. Those boundary conditions have to be in the wave zones. If you try and set R naught to 1,000, the wave zone has to move out extremely far, and the numerical integration will then accumulate a lot of error as it gets into the strong field. So you'll find the code is probably pretty good for results up to an R naught of 100, 200. It's probably okay there, but much beyond that, the results might start to get a bit ropey. So it's best in the kind of strong field regime, I would say. Okay, so having run that, that just ran through. It just quit the kernel at the end and just created that. So let's just quickly look at using that. So let me just set that up. Okay, so like Barry said, there's the H1 Lorentz folder. If we go into input, so that's the folder for the input, it's created that radial grid, which just contains those radial values that the code's going to run on. So this code is designed to run on a sort of clustered machine because it parallelizes trivially because each mode is independent. So it can do that. So you always have to run it with MPI run -n here. I'm just running with 2 cores. Interestingly, you can't run it with 1 because one of the cores is actually devoted to handing out the processes to the other cores. So the minimum number is 2. But what you then do is you can see you have to set a p-value, so that's R0, so p is coming from the eccentric parameterization, so the semi-lattice rectum, for our cases, that's R0. The code doesn't work for eccentric orbits, although if you look in the code base, you will find it has some stuff related to eccentric orbits, because that's where this code evolved from, a code that myself and Sarp actually wrote. So we chose 7, Lmax, let's just pick 10 modes. Where is the grid file input? So it asks where it is. So it's slightly funny. You do need to make sure these are consistent. This 7 needs to match this. If it doesn't, it'll do something weird. So just make sure you do that. And then where do you want to output? So I'm going to output in data and fields R7. You can make that whatever you want, but that's where I tend to put it, data, and then in here. And if you run that, as you can see, it computes a bunch of the orbital parameters, and then it's starting to compute the various tensor modes of the metric perturbation. As Barry said, it computes everything except the even static modes. So modes like the 2-0 and the 4-0 are going to be not so much missing from the data, but they're probably full of not a number or infinity or something. It's not quite true the code doesn't compute those. If you made a very small radial grid, I think it would. But there are issues using variation of parameters with those modes when you start very far out, because the static modes grow very rapidly. And so if you put boundary conditions very far out, by the time they reach the strong field, they are so big that the code is having problems, basically. And so instead, as Barry pointed out, what we do in that case is we kind of use a Mathematica code, which has to use extended precision sometimes in order to evaluate the static solutions. But all the radiative modes will work. And the E-odd static modes will work, and the monopole will work, and the dipole will work. Okay, so that's computed the mode up to L equals 10, so it didn't take too long. Typically, when we do actual second order self-force calculations, as Barry mentioned, we use something like 40 or 50 H1 retarded field modes. Okay, so if you go into data and fields R7, there are all the modes. And if you look at, say, the 2.2, it's 1.4 megabytes of data for the larger modes, and slightly less for the odd sector because there's less fields. So it's not a huge amount of data, though it does stack up once you have 50 L modes and you have many radius values. A few kilobytes. Okay, so so that's created these files, but how do you actually use those files? Well, if you go back into the notebooks folder, you'll find there's a notebook called load H1 Lorentz data. So I'll just open that up now and switch to that. Let's see, share screen. Good. Which kernel is that on? Kernels. Second kernel now. Okay, so similar, yeah, we use the simulation tools. Simulation tools are not crucial to any of this, but the notebooks are written to use it, and I do recommend it. It's very useful. So we load that. By definition, or we always set the mass of the primary to 1, just for convenience. And then there are some functions here which load the data. So if you decide to put your data somewhere else, then you'll need to modify this line, which is just with the data, and I call it fields R whatever. But then it'll load the data, and that data contains the field, and it's so the H1 field, the radial piece, and its first derivative, drH1, and it also contains the asymptotic values of the asymptotic amplitudes of the metric perturbation, from which you can do things like compute the fluxes. So we computed data, in this case, this function, as you see here, you can see the R0 LM. So we computed data at 7. So we'll just load those. Oops, we need to actually run this function first. So that will just load that data. And now, 7. there's the metric perturbation. So here, this is the metric perturbation between 2 and 200. It's actually computed up to 10,000. There's all the oscillations in the wave zone. Just for visual purposes, let's just do that. And then this command shifted has just moved it, just takes the whole result and shifts the x value by -2, and then plot a log linear plot. So this is the horizon or near the horizon. This is going out to infinity. Same thing again. Just plotting a different mode. So it's the 2-2 mode. And this is the 2-1 mode. So here you can see it's finite. The Lorentz gauge, the metric perturbation is continuous at the particle, but this is the location of the particle. And you can see the real part has a cusp and the imaginary part is smooth. And there's the wave passing out. So, yep, so I'll load any of those modes you computed. So that was the 2-2 and 2-1, but you can load the 10-10 or whatever you're interested in. And it's got the metric perturbation everywhere. That's in the Barak-Lusto-Sargo basis. I actually just opened an issue on this repository to actually add an example in here of actually converting that back into things like HTT or HRR, whatever. If you look in the various papers that are referenced, so look back at the Barak-Lusto-Sargo papers, they'll tell you how to convert these modes in this basis into things, other things you might find useful. Other things you might find helpful if you want a list of the coordinates. Again, let's do it for 7. That's the radial grid that was computed. So you can get that, extract that. And so just using simulation tools to list of coordinates gives you that. Because this thing, the data table, which is one of these objects created by simulation tools for manipulating data sets. And likewise, you can just, if you want to just get that object back to being a list, 7, then that's it in the standard list form. You'd have a Mathematica, so the radius and then the complex valued piece of the field. Finally, there's an example here where you can also extract the asymptotic modes of the metric perturbation. And so if you look at the formula in this paper by Sarp, it tells you how to relate that to the flux. So let's see if that works. And the flux is easily computed using another package from the Black Hole Perturbation Toolkit, the Tucholsky package. So you can go download that from the website. And the CoGeodesics package is needed. So you load that, create an orbit with the same value, 7. Compute the Tucholsky solution. And there you go, the relative difference between the two. Why is it giving me 2 values? Right, it's very small. It's doing it for different LLM modes, sorry. Yeah, so you can see that the flux as computed by the Lorentz gauge code agrees with the flux computed from the Tucholsky code as you hope it would. So that's a check. So that's all the examples I have the H1 code. If you have any questions, let me know, or if you have any issues, open them on the issue tracker. As I said, I'm going to add a section here that will convert the basis here to H alpha beta. So yeah, that's what I have. And then Barry, if you want to add anything, or Adam? No problem.
Yeah, I guess we've probably covered a lot, and it's just over 2 hours now, so people are probably tired hearing us. Shall I stop the recording now?
Mm-hmm.